open up the oxide passivating layer and then put the implants, all that kind of things. So naturally, we have to know how the dopant that you are going to use get changed, altered, profile-wise, concentration-wise. It is all in the dopant in silicon does all the tricks, right? They are the one who provides us all that energy levels for electrons and holes to move. So it's very important that we understand what oxide does to dopant, and this phenomenon has been modeled, and our friends are going to give you some details of how to model some of the dopant distributions. So I'm going to not elaborate too much because hopefully all those items will be covered in your simulations. Let's keep going. Oxidation system are conceptually very simple, like you know, but it can be very sophisticated, as I mentioned to you. Typically it's a hot wall type of furnace, which ranges in this kind of temperature range, very high degree of control, thermal control, so you can, and a very precise way of moving the wafers through the tubes, so that you have this exposure of high temperature, or depending on what oxide you're growing, to the dry or dry oxide, very nice sequencing of timing, ramping, when you are going to put the steam in, when you are going to take the steam out, when you are going to put the pure oxygen in, or oxygen diluted with nitrogen in, that kind of thing. They are precisely controlled within the furnace system so that you end up with the desired thickness of oxide as you pull it out from the chamber and with all the characteristics that you have. Okay? So that's how the oxidation system works. Controlled furnace recovery. Well, okay. The gases you typically use in the oxidation are oxygen, hydrogen, nitrogen. This is a source of chlorine. I told you my story of chlorine gas, but nowadays they use HCl as a dilutant. And argon, not too much used anymore. The water is steam, and it's injected by either steam or by oxygen-hydrogen combination. So there's an in situ moisture. When the so-called wet cycle, you bring in both hydrogen and oxygen. Otherwise, it stays oxygen in a nitrogen environment to regulate the partial pressure of oxygen. So you can regulate the rate of oxidation. Then it goes into the steam cycle where the hydrogen comes in. So it creates in situ moisture and grow the oxide fast. So in the kinetics, our friends are going to tell you about the model of the kinetics of steam oxidation versus dry oxidation. Yeah, particulate control we talked about is very important. Coarse bolts, they are very high purity coarse bolts. It's typically used to be cantilever loading and soft landing, etc. Vertical furnace, there are also vertical furnace, vertical oxidation tube. Again, not terribly popular, but there have been the cases, in many cases. Sometimes high pressure oxidation tube systems are vertical. That's another thing I was briefly mentioned. These are the so-called horizontal furnace system. These probably old 90, 2000 vintage. Now it's more sophisticated. Can we keep it? Yeah, I have a little bit of thing called high pressure oxidation. Then you have a very sealed systems where it gets pressurized to partial pressure of oxygen a bunch of times, about 4 or 5 atmosphere or 6 atmosphere times or 10 atmosphere times. so that rate of oxidation is faster. But if you use them from throughput point of view, it's an expensive gear. A lot of times people don't use them. Then there's always a problem of sealing and leakage and all that kind of things in a high pressure system. I do not believe the high pressure was at one time very strongly was there in the system manufacturing, but I think they have done that a little bit most of it. I don't think they use too much of high box type of oxidation anymore. Because for one reason, everything is thinned down. So, you know, you can grow it. Back in old days when you used to do very thick oxides and isolation, then throughput used to be important. Now it's not, you know, it's a very different way. Remember that thermal budget kind of question. Okay? Let's go. Yeah, let's go. Okay, here is a typical oxidation process in 1990s early days. Now, as I go walk through some of this processing, I may throw some examples. And this is a bit of a challenge to you, it's a bit of a challenge to Partho and Amritashish. So I will give you a real example of how things are done, back in, especially in those time frames. And then you have to model it. And then you have to come out with the answers. What this precise process yields, what is ends up to be. And this is a test of your modeling. It's a test of how good these models really are. Okay, so you're not a little bit modeling, but you know, as I said to you sometimes back, we start the model to get an idea, and then we iterate until we need exactly what we want. So that's the way industry develops technology, and model is important, that's in the first shot, but let's keep going. So you can see I've given an example here. And temperature, time, and everything. And then let's see when you simulate what you end up to. And I'll give you the answer then. The cleaning is so important. Yeah, it's important. In every oxidation, prior to oxidation, the cleaning is particularly very, very important. Because you are talking about very sensitive transistor technology, and interface is extremely important, contamination is extremely important, as you know. And we're talking very, very small levels of allowed defects and contamination. So almost to a point that you cannot measure. So that's why it's so important that cleaning is so important. So there's a fair amount of cleaning. The acid cleans are to get rid of the metallic particles, and the so-called H2O2 sulfuric clean is to get rid of the alkaline materials, temperature, time, and hot DI water, very clean DI water. These are extremely essential. And these are all done with, what's that called? The big tub switch, ultrasonic cleaners. These are ultrasonic baths. I forgot to write that down. But please make a note. All cleaning is done ultrasonic baths. They are specialized baths with ultrasonic facilities to stop and remove all minute particulates. Okay, these are not just you put it inside the bath and lift it up. They are a certain time, very specified time of ultrasonic agitation, so that it dislodges any possible minute particles from the surface. Okay? So all these baths are, all this cleaning is ultrasonically done. Okay, I'm going to give you a hint from the previous examples. Remember this, if you are growing this kind of oxide, which you grew back in 1990s class, I'll tell you tomorrow's class, tomorrow's special lecture, how we transitioned from LSI to VLSI. And why we ended up choosing this kind of thickness of gate oxide. Because prior to that, as you can well understand, the thickness of gate oxide was in the realm of 300 angstrom, 30 nanometer range. The 1 micron technology, which is the end of VLSI, used about 30 nanometer of EOT, the gate oxide thickness, although it's not exactly oxide. But we went down to this level to make ULSI happen. That's the process. I'm giving you the real process. And this could be a simple exercise of your dry oxidation kinetics that Partho or whoever you teach you to go through that simulation and see whether you get that oxide thickness. That's the recipe, real recipe. Okay? And that's why my last word is, let your simulation find out. Oh, I didn't. Yes, I made a trick. I didn't tell you the time. Because then I have given you everything, right? So you're going to do the simulation. And I'm going to enjoy your results. What's the time? Can you pick it up in the afternoon after you had some lunch? So this is a good time to start. So you pick it up in the afternoon. So have a good lunch.